In the second part of this, chapter 19, which deals with star formation, what we know is that when the interstellar medium's dark dust clouds gravitationally collapse, that's when stars form. The factors that affect this are gravity and heat, but also, which might not be quite as obvious, rotation of the cloud and the magnetic field that's present. So rotation competes with gravity's inward pull, as of course does heat. Heat is pushing everything outward, and the rotation is fast enough to overcome gravity, then matter in a rapidly rotating cloud would actually be flung out into space. Charged particles in a contracting cloud produce a magnetic field, and the field lines are compressed with the contraction, increasing the field strength and also altering the shape of the cloud. So the cloud, which might actually be, because of the rotation, might be flattened this way, tends to have kind of magnetic pinching, actually causes it to have a shape somewhat like that. In order to actually get a collection of atoms to have for their individual very, very small gravitational attraction to amount to anything, you'd actually have to have 10 to the 57th atoms needed in order for there to be enough of a gravitational pull to cause all these atoms to not disperse, to not actually just spread out in space. So once we get to that critical number, that critical mass of atoms, and that's a lot of atoms, 10 to the 57th atoms, then we actually can start to form stars out of that. For main sequence stars like the Sun, there's actually 7 stages of stellar evolution. So in the first stage, stage 1, you have this interstellar cloud. The temperature is about 10 Kelvin. There are approximately 1 billion particles per cubic meter, and the size of this thing is enormous. It's about 10 to the 14th kilometers in diameter. Now, what triggers the next stage, the actual start of the collapse, could be, and this takes approximately 2 million years for this to happen. It's either caused by, there could be a nearby stellar explosion, which is going to cause a pressure wave, or it's also the ionization, which is caused by newly forming O or B type stars that can actually squeeze the cloud beyond the point where the internal pressure can actually resist gravity. Another possibility is this also could be caused by dissipation of the cloud's magnetic field. That's another thing that would actually cause that contraction to occur. Now, in the second phase, this is the cloud fragmentation and collapse phase. Here the temperature is going to be about 100 kelvins. The central density of this collapsing cloud now is going to be approximately 1 trillion particles, 10 to the 12th particles per cubic meter, and the diameter now will have shrunk to 1%, or 10 to the 12th kilometers. When you're in phase 2, this cloud fragmentation, it may actually produce, in the end, maybe just a few dozen large stars, or it could be hundreds of smaller stars that are actually going to be produced out of this fragmentation phenomenon. So after about 30,000 years, fragmentation will stop, and we're going to enter stage 3. In stage 3, surface temperature is about 100 kelvins, but the core temperature now has risen up to 10,000 kelvins. The density is about 10 to the 18th particles per cubic meter, and the size of this collection is 10 to the 10th kilometers in diameter. And after about 100,000 years, then we go into the 4th stage. Now, the 3rd and the 4th stage combined collectively are known as the Kelvin-Helmholtz contraction phases. You should know that. Kelvin, named after Lord Kelvin, and Helmholtz, another physicist. Phases 3 and 4. So in stage 4, we actually have the first object that we would call a protostar. And this means that we actually have, we can actually see what appears to be a photosphere. So although it's actually not hot enough to undergo fusion, There's still a lot of gravitational energy that's being released, and that causes the surface temperature to heat up to about 3,000 kelvins. The core is now at a million degrees, a million kelvins. The density is 10 to the 24th particles per cubic meter, and the size has now shrunk to 10 to the 8th kilometer diameter. So it flattens, it's flattening out as this protostellar disk. So as this thing is rotating, in order for angular momentum to be conserved, this thing has to continue it's actually going to revolve faster, and it's going to continue to contract. That is, contract this way. So it's going to move, it's moving, and you can see that all along, it's moving to a smaller and smaller diameter. So it's actually rotating more rapidly. The other thing that I want to mention is that a stage 4 protostar is going to have very, very great apparent brightness. And that's just because of its huge size, not because it's incredibly hot, because it's not as hot, nearly as hot as a star. Now, we can actually start, once we reach stage 4, we can actually start to plot an object, a stage 4 object, a protostar, can be plotted out on an HR diagram. Anything before that, we can't really put it onto an HR diagram. But here now we can start to plot these things out on HR diagrams. And what that will enable us to do is, once we see once we get through not just the formation of stars, but once they end their lifetime, they're going to die out in some way. So we can actually, by looking at the HR diagram, we can actually determine where a star is within its lifetime. As I mentioned before, that on an HR diagram, a star is going to spend most of its time, most stars are going to spend most of their time on the main sequence. So, you know, they're going to be here. But stars enter from outside of the main sequence, then they don't move up or down the main sequence. They stay wherever they are until they've actually exhausted most of their hydrogen, and then there'll be, depending on their mass, there'll be a number of different possible things that can happen to the star. But at that point, the star will actually move off of the main sequence. It will no longer be a main sequence star. So we're going to, and that will be important for us to understand that, in order to be able to comprehend the fact that HR diagrams are going to be useful for us to be able to understand something about the evolutionary history of stars. So after about 1 million years, then we're going to get to stage 5. Now the surface temperature has again increased. Now it's up to 4,000 kelvins, and the core is now heated up to 5 million kelvins. Density is 10 to the 28th particles per cubic kilogram. Diameter now has shrunk to 10 to the 7th kilometers. And now this evolutionary process is going to start to slow down. It's going to take us another 100 million years to reach the stage 6. And here the surface temperature will be at 4,500 kelvins. The core temperature will now be up to 10 million degrees. And once we get to stage 6, at this temperature of 10 million degrees, that's the critical temperature at which proton-to-proton fusion can occur. So the hydrogen, is going to start to fuse, and we're going to, this is actually going to ignite as a full-fledged star. So the protostar now becomes a star. Its central density is 10 to the 31st particles per cubic meter, and diameter is now 2 times 10 to the 6 kilometers. And after about 30 million years, a star the size of the sun will actually reach, it will be at the point of maturation where it is now becomes a main sequence star. And it's going to have a surface temperature of about 6,000 kelvins, a core temperature of about 15 million kelvins, a density of 10 to the 32nd particles per cubic meter, and a diameter of 1.5 million kilometers. So the stages 4 through 6 are known as the Hayashi track. This is stages 4 through 6, and I'm actually going to put that out on, try to draw an HR diagram so you can see where this is heading. This is actually in your book. Probably find a better diagram than the one that I'm able to draw, just for purposes of illustrating this. Plotting temperature on the x-axis, and we're plotting luminosity in solar units on the y-axis. So we'll start we'll have points here at 10 to the minus fourth sols. That's the luminosity of 1/10,000th of the sun. The next point up will be 100th, 10 to the minus second. Then 10 to the 0, which is the sun. 10 to the 0 being 1. That will be the sun's luminosity. Then we'll go up. We're going up by factors of 2. 100 times the sun and 10,000 times the sun, 10 to the fourth. So these are the luminosity. So these all are luminosity units. And on the x-axis, we're going to be plotting temperature, but we can also put in our designations for the classification: O stars, B stars, A stars, F stars, G, K, and M. And these temperatures, won't put all of them in, but for M, it's about 3,000 kelvins. It's the coolest. The G is at about 6,000. A is about 10,000. O is going to be around 30,000. And we could have stars that are even hotter than that would go off in this direction. Okay. Now, one other thing that I want to put in has to do with I'm going to put in some dotted lines, diagonal lines. These are going to represent the size of the star, the radius of the star, how big the star is. So we have one line that would look sort of like this, and we have a couple parallel lines. Another one that would be, let's say, up about here and extend up to about here. Another line that will go from about here to here, and then we'll have another line up. So along these lines, these lines are going to represent different radii. So for a star that has the radius of the sun, we'll call that 1.0 solar units, solar radii. Then this would be the line for a star that would be 0.1 solar radii, and this would represent 10 solar radii, and this would represent 100 solar radii. What we're going to find is that if we look at the Hayashi track, so that is stages 4 through 6, we can see for a star that has a mass the size of the sun, what it looks like is this. At stage 4, its temperature is somewhere around 4,000 degrees, and it's going to fall when we actually plot it out. Its luminosity will be up and around, maybe somewhere around 10 squared. It's going to be somewhere around here. So that's where that will be the stage 4, that's where it will actually enter onto our HR diagram. And then it's going to move down as it's through its evolutionary history. It's going to move down as it moves to stage 5, this one solar mass sun. So this is for a star or a protostar that is one solar mass. It's going to move over. It'll be now a K type of object. Once it gets up, and its diameter will be about 10 solar radii. So it'll be somewhere around here, and this will be stage 5. And then it's going to go probably somewhere. It's going to move down like this. So it's moving like that, like that. So somewhere about here will be stage 6, and then it's going to hop. It's going to hop over and actually land on the line that is actually going to represent its position, main sequence through here. But then it's going to become a main sequence star. So the main sequence it'll hop onto the line right over here, somewhere about here, and it'll be a main sequence star. So it'll be, it'll actually fall right on the main sequence, and that will be stage 7 when it actually hits the main sequence. We haven't actually gotten to that point yet. But what I wanted to show was that if we look at these Hayashi tracks, what we'll see is, depending on the This is for a star of approximately the size of our sun. But if we have a star that is, let's say, 3/10 of the sun's radius, it's going to have an almost identical track, except that it's going to be displaced to the right. So we might see something where that ultimately is going to fall onto the main sequence. It's going to be, it's actually going to be somewhere around, oh, I don't know, maybe around here when it actually falls into the main sequence. And then a star, so this would be 7 for that star, and it's going to have a similar kind of look. It's going to look like that. But when it actually becomes a main sequence star, that 0.3 solar mass star is going to be somewhere between maybe a K and an M class star, where the sun or stars of that size are going to be G class stars. And then finally, you could get something that would probably be an F, or maybe somewhere between an F and an A at about 3 solar masses. And so that's going to actually, that will come onto the main sequence somewhere around here. And, and again, it's going to be a similar kind of thing, 6, 5, 4. So it's going to look, something like this, and it hops over. So that I just wanted you to, and you can see, like I said, a better picture of this in the book. But the main sequence line predicted by theory, and this is actually borne out by observations over 20,000 stars. And this is called the zero-age main sequence. And as I said before, a star, once it gets onto the main sequence, it doesn't move up and down the line. It stays at that position for most of its life. It's only when it reaches the end of its hydrogen burning that it will move off of the line, but it doesn't move up and down the line. Whatever position, which is actually, as I said before, is dependent on the mass, that's going to determine where the star will actually lie along the Hertzsprung-Russell diagram. Okay, some cloud fragments are too small to even become stars. So in order to initiate hydrogen fusion, you need to have a mass of at least 0.08 solar masses. That's about the size of 80, so that's 80 Jupiters, so 80 times the mass of the planet Jupiter. Now objects between 12 Jupiter masses but less than 80, anything less than 12 is going to be a planet. But between 12 and 79, you can still get some pretty hot objects, and these things are known as brown dwarfs. They're not hot enough to burn hydrogen, because that's going to require temperatures, as I said before, of at least 10 million degrees. However, their core temperatures are hot enough, in fact, to induce fusion of deuterium. Remember, this is hydrogen. It's got 1 proton and no neutrons, but deuterium has 1 proton, the deuteron has 1 proton and 1 neutron. So it's actually easier, requires less energy to fuse these two things than it does to fuse hydrogen, to fuse protons. So deuterium, that can actually, with brown dwarfs, the deuterium, which was going to exist in smaller quantities, can actually ignite. It's going to burn at a lower temperature, but it will still be, nevertheless, a thermonuclear reaction. These objects, therefore, are not as hot, and the deuterium burns off relatively rapidly. And once all the deuterium is used up, unlike in larger stars that actually undergo hydrogen burning, once all the deuterium is used up, that's the end of the line for that star. So what we're seeing with these brown dwarfs are stars whose fires have basically gone out. They don't fall back to to the temperature of interstellar space. They still remain hot for very, very long periods of time. But there's no longer a nuclear furnace that's powering them. The estimate of the number of brown dwarfs in interstellar space is still relatively small compared to all the stars. I said the number of stars is probably on the order of 10 to the 22nd stars in the observable universe, and it's estimated there are only about 10 to the 11th, which is still a nice sized number. That's 100 billion or something like that. But there are only that number of brown dwarfs estimated in the universe. Now, what evidence do we actually have for things like cloud contractions, etc.? Well, one of the things we can look at is that we can look at a contour map of the radio signals that are actually given off by things like formaldehyde. So I mentioned formaldehyde before. The formaldehyde molecule, just like carbon monoxide, has transitions that can be seen in that 21 centimeter band. Formaldehyde is another molecule that's emitting, that has transitions that occur in the radio frequency. And by looking at that, it's possible to see a region of space where, even though you might not see any visible light there, you're seeing the presence of formaldehyde molecules in a much greater abundance than you do in nearby regions. So, for instance, if you look at the nebula, the M20 nebula, which is undergoing, you can find evidence in there of star formation anywhere from stages 1 through 3, and that, a lot of that information is just gleaned by looking at the contour map of the formaldehyde molecules that are present in that region. The Orion Nebula shows evidence of cloud fragmentation. Another object in Orion that's called the Beckman-Neugebauer object. This is actually in the core of the Orion molecular cloud, and it's got an enormous luminosity, equal to 1,000 solar units, 1,000 suns. So this is evidence for a high-mass protostar, and this protostar is believed to be around stage 4 in its development. There's other objects in Orion that have infrared signatures that indicate that they're at stage 5 in development. Now, another interesting thing are that when you have these protostellar objects, they actually produce very, very strong protostellar winds. And the winds, in some instances, result in a bipolar ejection of jets of matter. These things are called Herbig-Haro objects, abbreviated HH, after the individuals who actually catalog these kinds of things. Herbig-Haro objects. And so what this is basically you've got a protostar here. It's giving off a lot of light, and it's rotating very, very rapidly. And from the center of this, there's actually ejection of a mass of matter that can be seen. It's bipolar, which means it's moving this way. There's a jet of particles moving this way, and another jet moving that way. And this is something that can actually be observed. And one example is in the star that's cataloged as HH30, and these two jets are referred to as HH1 and HH2. So that's also evidence of what happens during cloud contraction and fragmentation, formation of a protostar. Shock waves from emission nebulae, planetary nebulae, which we haven't talked about, but we'll get to those a little bit later on, or supernovae explosions, which we also haven't talked about. These things cause compression and star formation. Also, old stars in their death throes can also trigger new star formation. Collapse of a cloud can give rise to star clusters. Now, there are various kinds of star clusters that occur. There's one particular type that is kind of loose and irregular in terms of structure, and these things are known as open clusters. So open clusters are described as loose, irregular. An example of an open cluster is the Pleiades, which are actually one of the few things that is very, very characteristic in the sky. It almost looks like a little miniature dipper to me when I look at it. But you can see pictures of the Pleiades. And that particular collection of stars, there's, I think, 7 stars that make up the main part of it. But if you're looking at it through a very powerful telescope, you would see that it's actually a cluster of stars. There's a lot more stars in it. So that's an example of that. Now, the number of stars that may be in this kind of a cluster could be as few as maybe a few hundred stars, and they could be up to tens of thousands of stars. less massive type of structure, but more extended. These are called associations, and these tend to be rich in O and B type stars, and there's also some associations that have a lot of T Tauri stars, and they're just called T associations. If there's a lot of remember that the T-type stars are stars that are really in their infancy. So when we see those things, they're known as T associations. Also, the other kind of cluster that you see are something known as globular clusters. And unlike these other ones that are loose and irregular, here all the stars are kind of put together into a thing that almost looks like a sphere. And you've got many stars in these things. It could be hundreds to thousands of stars, somewhere between in the region of 10 to the fifth, even maybe a few million stars that might be present in a globular cluster. Now, if you actually look at an HR diagram of open clusters, you'll see that in an HR diagram of an open cluster, all the stars in the cluster will actually lie right along the main sequence. But if you look at the HR diagram of a globular cluster, you'll find out that what you get there is the part of the main sequence that has these more massive stars, that's kind of gone. And you'll see a lot of stars of lower masses. And then you'll see a bunch of stars out here, and stars in the red giant region. There'll be a lot of stars out there, and there'll be stars off here and here. But you'll see a lot of red giants. And the red giant stage is a much later stage of in a star's lifetime. But we'll talk about that later. But when you see red giants, I mean, that's telling us that these are older stars. So this in the globular clusters, we're seeing older stars, and we're not seeing these heavier stars in the main sequence, which would seem to imply that these stars are leaving the main sequence and they're becoming red giants. And in fact, that is what's happening. So really, when you're looking at globular clusters, I said there's no upper main sequence stars, and there's really nothing beyond about 0.8 solar masses. So the stars that you're seeing all have masses a little bit less than the mass of the sun in these clusters. Globular clusters have the oldest stars in the galaxy. Now, the tidal gravitational field of galaxies like our own Milky Way slowly strips away outlying stars from a cluster, and encounters with heavier stars actually eject lighter stars from the cluster as well. So most open clusters actually will break apart in a few 100 million years, depending on the mass of the cluster. And associations may last for only perhaps a few tens of millions of years. And a few very massive open clusters may be as long and maybe as much as 5 billion years old. Globular clusters could be even older than that. Well, that concludes what I want to say about this chapter. Again, thanks for your attention and your patience. Thanks again.